So we've learned about multiplicity, and we've learned about how that relates to entropy through the equation S equals KB ln W. We only touched on entropy briefly, and in this lecture, we're going to go through some thermodynamics that are relevant to this course. Specifically, we want to focus on free energy because that's going to be very important for future lectures. So the last topic was pretty long, and we're just going to go through a quick recap of what's most important. So basically hydrogen bonding and their energies, or energetics. At the end of this lecture, we're going to go through an example and combine everything together through some two-level systems. But before that, we have to go through a few relevant terms and definitions in thermodynamics, just so that we understand what free energy is and how it relates to entropy. So after that, we're going to take a look at modeling two-level systems and interactions between two separate systems. So before I get started, I want to review hydrogen bonding again, just so we remember it for some practice later on in this chapter. And in this lecture, we want to discuss energy. So that means understanding the law of increase of entropy and the fact that it's dependent on multiplicity W. So a few students asked some really good questions last week, and basically it has to do with what the physical meaning of W is. So in mathematics, multiplicity is the number of repeated elements in a set. Once we move into biophysical modeling, we're not just interested in repeated elements, we want to take a look at energy. So when we take a look at energy, we're going to say that something, like a protein, has X number of states with the same energy. We call this degeneracy, the number of states with the same energy level. So keep in mind there is a difference between multiplicity and degeneracy, but in our course, they're going to go hand in hand with each other. So just note that degeneracy means the number of states with the same energy level, whereas multiplicity is just a mathematical definition of microstates within a state. But in modeling, let's think about what we would prefer. Would we want high degeneracy or low degeneracy? This is something that we'll tackle in the next few chapters, but in this unit here, we're going to have a general overview of whether we want high or low degeneracies. So keep in mind, since proteins have function, that means they should only have one particular conformation or one preferred shape so that they can execute that function. And because they have one preferred shape, it should mean that the degeneracy should be 1, so that a favorable shape can emerge as the winner over other conformations. So when we talked about hydrogen bonding, we looked at multiplicity W being the total number of fully H-bonded configurations of the central molecule. In other words, how many favorable directions can the central H2O molecule face? So I'm introducing the word favorable here because we're going to hear a lot of that in the future. So favorable versus unfavorable interactions. So the general idea is that when you have a favorable interaction, you're going to have positive energy. And when you have an unfavorable interaction, you're going to have negative energy. So that's stuff that we will talk about, I believe, in the next couple of units. So the two hydrogens can face any side or edge of the tetrahedral shape. So looking over here, we have the central H2O molecule, and the two hydrogens are facing two of the edges. And we show through our exercise how many preferred configurations there would be. So let's go through this quickly. So we looked at hydrogen bonding in water. So let's assume that there's a polar molecule in the center, which is our H2O. There's also a whole bunch of polar molecules surrounding it. So we have 4 possible interactions with the central water molecule. So polar molecules have favorable interactions with other polar molecules. So that means the central polar molecule can be oriented in any direction where there are two adjacent polar molecules as well, which is pretty much every single side of this tetrahedral shape. So since we have 6 different sides, that means we have a multiplicity of 6. So 6 different possibilities of interactions that are favorable. So remember, polar-polar interactions are favorable, but polar-nonpolar interactions are unfavorable. So this comes in very handy once we start doing protein analysis. Afterwards, we looked at what happened when we introduced an oily thing. So what if we introduced a non-polar substance in one corner? We chose the back corner. In order to maximize your favorable interactions, our 2 hydrogens are going to now want to face any edge that doesn't have that non-polar molecule. That means there's 3 edges that are free from the polar molecule, faces 1 or sides 1, 2, and 3. The other ones, 4, 5, and 6, they're attached to the nonpolar molecule, which means that there's going to be at least 1 unfavorable interaction if the central H2O molecule faces one of those edges. So that means there's 3 edges left that are solely made up of polar molecules at each end. So W, or multiplicity, equals 3, and you can calculate the entropy to be Kb ln of 3. On the flip side, you can always calculate how many possible unfavorable interactions there could be, and in this case, there's 3 unfavorable interactions at the back, so W is also equal to 3 for unfavorable interactions. So we're going to do a full analysis in future chapters, but if our central H2O molecule here, so these 2, they're polar molecules. If they interact with non-polar molecules at the back, we call this an unfavorable interaction, and that means there's some sort of negative energy or negative interaction energy that's taking place. And the more negative energy you have, the less likely that conformation or geometry is preferred. Okay, so this slide has to do with analyzing what we just discovered. We found out that multiplicity decreases when we introduce a nonpolar molecule, which means entropy decreases. So it's because also that basically goes against the law of increase of entropy. So we want to figure out why that is. It's because the law of increase of entropy pertains to an untouched system, which means we get higher entropy with spontaneous reactions. In this case, we've actually introduced a hydrophobic substance or nonpolar molecule to the system. So we've changed the system and we've inputted some energy. And if we do that, it means that there's going to be, a reduction in entropy that could be possible because the system becomes more ordered from the disorder that we've introduced. So there's some wiggle room because we've changed the system. And here are 2 examples, one that's an analogy and one that's a little bit more specific to the course, just so that we can wrap our heads around this. So let's say that your room is really messy because we all work from home now, and you're trying to organize it. So you have to expend energy in order to clean up and organize your room. But in fact, your room is now more organized. You've decreased the entropy of your room, but you've actually inputted energy into organizing the room. So we've made changes to the system, which allows us to create some order from the disorder. Now, with hydrophobic molecules being added to water, we use the same analogy in that we've inputted some energy into the system. And with hydrogen bonding, the nonpolar molecules are going to rearrange themselves to create barriers between 2 types of molecules, polar versus nonpolar. So out of some disorder, there will be order because we've introduced energy into the system. So let's get started with thermodynamics. We're going to go through a quick definition and then a few useful equations. So keep in mind, I won't focus too much on thermodynamics for this course, but it is really important to understand what free energy is. So the definition of temperature gets more and more complicated as we look into thermodynamics. At the first level of understanding, we can define the temperature as what we'd measure with a thermometer. At the second level of understanding, we can say that the temperature is the thing that's the same for two objects after they've been in contact for a while and have achieved what's called thermal equilibrium. And we say that energy is exchanged in order to achieve thermal equilibrium. So that's the next definition of temperature, a little bit more detail, but we can be even more detailed than that. We can define temperature as a measure of the tendency of an object to spontaneously give up energy to its surroundings. So, in other words, when two objects are in thermal contact with each other, the ones that will spontaneously lose energy are going to be the ones at higher temperature. You've probably heard objects of higher temperatures are going to share some of their temperature with objects of lower temperatures. This is the same idea. So, we're going to be looking at specific examples of this in this lecture. And in order to understand all this, we want to first start with the ideal gas law, which you've probably all seen before. We know that it's PV equals nRT from other courses. So it has the following parameters. P for pressure, and you can have different units for it. You can have 1 atm versus 1.013 times 10 to the 5 pascals. You can have volume in meters cubed, or you can also have liters, or 0.1 meters cubed. The N represents the number of moles of gas, and we're going to focus on the N in a bit, because we want to be able to tie the ideal gas law back to entropy somehow. So we have N being the number of moles of gas, we have capital R being the universal gas constant, and you have temperature T in Kelvin. So this is all great. It's very useful in chemistry, but we want to be able to relate it back to entropy and free energy. So why don't we redefine it using some parameters that we've already studied, just to link it back to something we're familiar with. So the first step is to focus on that N, the number of moles that I mentioned before. You can redefine 1 mole using Avogadro's number, where capital N is the number of molecules, and you have Avogadro's number for the number of molecules in a mole. So you have N being equal to capital N over Avogadro's number, and then you can rewrite it, rewrite the ideal gas law, so you have PV equals to capital nRT over Avogadro's number. Then we notice that the Boltzmann's constant, Kb, is defined as the ideal gas constant divided by Avogadro's number, which is 1.381 times 10 to the negative 3 joules per Kelvin. So now this is perfect because we can replace R over Na with Kb. And we now have a new equation for the ideal gas law that has Boltzmann's constant in it, and N being the number of molecules. So now let's go back and take a look at entropy again. The second law of thermodynamics states that the total entropy of an isolated system is going to increase over time. So that means that your multiplicity is going to tend to increase. We already know that entropy is S equals to Kb ln of W, so over here. We define multiplicity as the number of microstates within a given state mathematically. And the next thing I want to mention is that we choose ln of W to be unitless. So when you're doing calculations with entropy, keep in mind your multiplicity is unitless. And we also include Boltzmann's constant in front so that we can give it a unit. So now, because Boltzmann's constant is in units of joules per Kelvin, we have that as the units for entropy as well. So we've gone through a bit of the mathematics for entropy. Now I want to share how we can visualize entropy. So with all this talk, we first want to define entropy as also the disorder of a system. But sometimes it may not appear that way. So let's look at a couple of examples just to solidify our understanding of entropy from a conceptual standpoint. So when I shuffle a deck of cards, we end up with disorder. So that means the cards are everywhere and they're a mess. So I'm pretty sure we can all agree that shuffling the cards is going to increase entropy because it increases the number of possible arrangements of the cards. Now we move on to the next example. What about a glass of crushed ice versus a glass of water? Which one's going to be more disordered? So there's two ways of looking at this, and there isn't really one correct answer, but all I really want to share is that there are different ways of looking at a system, and depending on which way you look at a system, it can be disordered or ordered. So looking at a glass of crushed ice versus water, crushed ice is obviously more disordered because your ice is just crushed into tiny pieces, whereas you have a nice glass of water that seems nice and molded to the shape of the cup. But when we take a look at ice itself and water itself separately, it's important to note that water is going to have more entropy than ice because there's many more ways of arranging its molecules versus ice, which only has a limited way of rearranging its molecules due to its solid structure. So these are just broad generalizations that are just meant to give you a quick visualization of entropy and disorder, and the fact that depending on how you look at a system, or two systems, one can be more disordered than the other, or vice versa. Now onto the main part of our lecture, entropy and thermodynamic potentials. So when we take a look at chemical thermodynamics, we're looking at chemical reactions that are constrained by the laws of thermodynamics. That means the system is going to end up in a different state than when it started. In chemical reactions, the system is not isolated, but rather interacting with its surroundings all the time. These interactions can be thermal or mechanical, and the energy of the system usually isn't fixed. But even though the energy isn't fixed, we're allowed to fix certain parameters like temperature and pressure. So let's go through a few terms. Enthalpy, H, is the energy needed to create a system, plus the work needed to make room for it. So keep in mind, H, enthalpy, is defined as U plus PV. And we'll define all of these terms afterwards in a little chart. So we have H equals to U plus PV. At constant pressure, the work done by a thermodynamic system can be defined as the pressure, which is a constant, times the total volume represented by this integral here. So because we can hold pressure constant, we can factor this out. So we have W equals P times the integral of a differential volume element, which is simply the volume of your structure or molecule, and that means W equals to PV. So W equals PV here means the work needed to make room for the system. The Helmholtz free energy, F, is the energy needed to create a system minus the energy you get from the environment. So F equals to U minus TS. This free energy is very important to remember because we'll be using this a lot. So let's define this energy that you get from the environment. It's basically the heat that you can obtain freely or from a specific temperature in your environment. Entropy is in units of joules per Kelvin. So if I want the energy that comes from the environment, and the environment has some disorder, then the entropy in units of joules per Kelvin can be converted to joules if we multiply by temperature. And that's where we get TS. So when we multiply entropy by temperature, we get joules of energy. So once you subtract TS from U, you're going to have the energy needed to create the system from scratch. Now, the Gibbs free energy is different in that it is the work needed to create a system at constant pressure and constant temperature. So because of that, we have these two terms, TS and PV here. So to clarify, now we have U being the energy required to create a system in the absence of any temperature or pressure changes. PV was introduced as the additional amount of work required to create room for the system, and TS was introduced as the amount that's already existing in the environment that comes from entropy. So Gibbs free energy accounts for all of this, and that means we have G equals to U minus TV plus PV. And now we ask a question, why is Gibbs free energy important? It's important because it's going to tell us the maximum amount of work that can be obtained from a chemical reaction. So here's a helpful chart for you to remember these equations in the future. You essentially pick a starting point and an end point and use the arrows to create your own equation. So let's say I want to start here with internal energy and I want to arrive at Gibbs free energy. It means U has to be subtracted by TS to arrive at F, and then you have to add PV to arrive at G. So you get G equals to starting at U minus TS plus PV to get to G. So these are useful equations to remember in case there are questions on an assignment or even on an exam that asks you to calculate the Gibbs free energy or the Helmholtz free energy of certain reactions or interactions. So we briefly went through some key terms in thermodynamics. We now want to move on to analyzing two-level systems and their interactions. To start off, we obviously know that atoms and molecules have energy, so the more energy levels or shells an atom has, the more potential it has for greater energy because of the presence of a greater number of electrons. So, a simple comparison, this element is obviously going to have more energy than this one, just because of the presence of more electrons. So looking at the valence shell, we can consider a ground state, which is its natural state. And there can also be an excited state where these electrons move on to a higher energy level. So why don't we use two different types of levels to do some analysis? We can use a ground state and we can use an excited state to describe a two-level system. So why don't we take a closer look at that? So in this picture, we have a system A. It's called a two-level system because there's a ground state and an excited state. We can assume that every single one of these circles has, on the ground state, has an energy level of 0. So we can actually state that here. Epsilon, the amount of energy, is equal to 0 for each of these states. And for these two circles that are on the upper level of the two-level system, they have an energy level of 1 for each of them. So we have 8 circles with an energy level of 0 and 2 with an energy level of 1. So the question I want to ask is, what is the total energy U of the system if epsilon is the energy value for each circle? So 8 times 0 is just 0. All of the circles on the ground state don't account for any of the total energy. They're just 0. But then you get these two circles that are at the upper level of the two-level system, and they have energy values of 1 each. So that means 1 times 2 is 2, and your total energy of the system is just going to be 2. Now let's ask ourselves, how many different ways can we distribute the particles if the total energy doesn't change? So we figured out that if we have 2 circles on the upper level, we have an energy level of 2. But how many different ways can we rearrange this so that there's always 2 circles at the top? So that means we're going to have to try and find the multiplicity of system A. So we call this WA. And we want to see how many ways we can rearrange this so that U equals 2 all the time. So this is where the mathematical description of W comes in handy. We have a total of 10 circles, so we have n equals 10. We have n0 equals to 8 for the number of circles at the 0 energy level. And we have n1 being the number of circles at the second energy level with a value of 1. So applying our equation for multiplicity, we have capital N divided by our 2 options, factorial versions for each. And we plug it into a calculator and we get 45 as our multiplicity. So hopefully this makes sense in that we can calculate the multiplicity of a system or a 2-level system by modeling it as a ground and excited state. So we have WA equals 45. Why don't we introduce system B? So let's introduce another system and let's take a look at that one. And after we do, we'll be able to see what kinds of interactions system A and system B can have together. So looking at system B, let's say this one has 6 circles in the ground state and 4 circles in the excited state. That means that the total energy of the system is 4. So that's pretty straightforward. We now have the total energy for both systems A and B. So I have the multiplicity for system A. Should probably figure out the multiplicity for system B as well. So we're going to ask ourselves the same question again. How many different ways can we rearrange these circles so that 4 of the circles are always in the upper state? So we have n equals 10 this time, n0 is equal to 6, and n1 is equal to 4. We plug our values into the equation for multiplicity. We call this WB now, and we get 210. So that means there are a lot more ways to rearrange this. And that means the entropy for this is going to be higher. So now that we've looked at the 2 systems separately, we can start combining them. When we take a look at the interactions between systems, we first have to determine how they're connected to each other. So are the 2 systems connected through an insulated barrier or not? So we have this here. So this line is drawn between system A with a total energy of 2 and system B with a total energy of 4. So we're going to take a look at what happens if this barrier is insulated and if this barrier is not insulated and they are in what's called thermal contact with each other. So in an insulated combined system, we can assume there's no energy exchange. Both of these systems are completely separate. They're on their own. They're just kind of stuck together as one piece. So the total possible combinations or total multiplicity would be the 2 separate multiplicities multiplied by each other. So we have the total multiplicity being WA times WB is equal to 9450. So that's the total multiplicity of the system. Now we introduce thermal contact, and that's when heat exchange can occur between the 2 systems. If there's thermal contact, their total energy is going to be the sum of the 2 individual energies. So I have 2 here and 4 here, so the total energy of this one system in thermal contact is going to be 6. So I've forgotten a 2 here, but the total energy is going to be 2 plus 4 equals to 6, and that means we can have a total of 6 molecules in an excited state. So what does this mean for multiplicity, and how can we calculate it? So it's actually a little bit more complicated than you would think. We're going to start with the fact that we know we have U equals 6. So how many ways is it possible for U to be equal to 6? Well, if we take a look at this, number one, there's always an option that no energy exchange occurs, and that there's always going to be 2 here in system A and 4 excited states in system B. So that's one option. The second option is going to be if there's thermal energy exchange from A to B. So that means instead of having an energy level of 2 over here, A can drop to 1 and B can go up to 5. The last option is if B transfers some of its thermal energy over to A, so then UA is going to be 3 and UB is going to be 3. So we're going to analyze each of these and try and figure out which kind of action or heat exchange is most probable. So you can probably use logic to figure it out, but we actually want to figure out why through multiplicity and an explanation through entropy. So these are the three different ways for heat flow to occur. So no heat flow from A to B, or heat flow from B to A. And if you have heat flow from A to B, so that means UA is going to drop to 1 and UB is going to go up to 5, you get a total multiplicity of approximately 2,500. But the other way, from B to A, you get about 14,000. So that means that this option is going to have the highest entropy. And as we've learned before, all systems are going to tend towards a state of higher multiplicity or higher entropy. So when I ask, or when we're trying to ask you which reaction or which scenario is the most likely, you should be able to calculate the different multiplicities, and then from the answer, find the one with the greatest multiplicity and say, this one is the most likely. So give it a try going through these two calculations to figure out 2520 and 14,400 so that you can find the answer yourself, using number 1 as an example because we went through that. So after you do the calculations for all the possible scenarios, we then have to take a look at which scenario is most likely. So like I said before, any system is going to tend towards larger or greater entropy. So the option with the highest multiplicity would be the most likely. So we see that heat flow from B to A gives us a multiplicity of 14,400. So we can predict that this is the most likely scenario to take place spontaneously. And that means it's going to go towards thermal equilibrium because UA is going to become 3 and UB is going to drop down to 3. So we can now take a look at the energy per molecule to determine a relationship between that energy and the temperature of the system. So that means we have E over N, so we get 2 over 10 and 4 over 10 for systems A and B respectively. From this, we can see that the heat is always going to flow from a high temperature system to a low temperature system. So the energy per molecule in system B is higher than the energy per molecule in system A. So any system that has higher energy, which also means it's going to have a higher temperature, it's going to move towards a system of lower temperature, especially if they're in thermal contact. If there's a question like this, like a trick question that's asking you about the energy exchange, if it's insulated, then you can just say no energy exchange occurs. So hopefully all of this is making sense so far, because we now finally get to connect multiplicity and probability together. So we know this equation for entropy. But we're going to now introduce the idea that probability is proportional to multiplicity. So in statistics classes, you've probably have covered this before, but in this case, we know that probability is proportional to multiplicity, and we can get this equation, e to the power of s over kb, as an expression for probability. So we'll only cover this equation briefly, and you can apply this equation in assignments if you wish without any explanation, apart from the fact that we can use it to calculate probability. So now let's ask some follow-up questions. What happens if the two systems are of different sizes? So what happens if, for example, I no longer have 10 circles in system B, but maybe 50 circles in system B? So it's going to be a bigger system with more molecules. So all of the calculations remain the same. The assumption is that the combined system is still going to tend towards a state of maximum entropy. So do the calculations and just find the scenario where W is maximized. So then, how can we describe system A irrespective of the other system B? So what this question means is, how can we express system A using all of the terms that we've introduced before? So we can use our Helmholtz free energy equation, F equals U minus Ts. And with this, what we can say is that as entropy increases, we're going to get a larger negative number here, which means our free energy decreases. And what this tells us is that your free energy is going to be minimized for your most probable case. And that's super important when we move on to protein folding. So now to recap, this means that a system is going to tend towards its minimum free energy state. And in other words, we can state that the minimum free energy state is the most probable. And now I can finally introduce the word degeneracy. So we're going to see this in future lectures, but degeneracy is going to mean the number of minimum free energy states that the system can have. The lower our degeneracy, the more likely the system is going to tend towards that state. So multiplicity and degeneracy are going to be slightly different. In mathematics, if you interchange multiplicity and degeneracy, it's okay. But here, we're going to be calculating the multiplicity of degeneracy. So that means how many degenerate free energy states there will be. The lower the better, because that basically means there's going to be a higher entropy. So here are some probability expressions for a system to be in a certain free energy state. So these we will go through for the examples and live lectures. But for now, that's pretty much it for an introduction and overview of free energy and entropy and how they're related to each other. So just as a summary of what we've done through this, we have thermodynamic potentials and identities. We went through potentials F, G, H, and U. We can also derive equations that relate all four, so that's important. We looked at the multiplicity and energies of two-level systems. So remember, be familiar with how to calculate the multiplicity of a singular two-level system, and also be familiar with how to calculate the entropy or the multiplicity and the total energy of two systems interacting with each other. So that covers all of this. And during the live lecture, we'll go through an example, and through the assignment, we'll have a challenge question where you can apply your knowledge of probability to different types of systems.